So what we're going to do here is talk a little bit about a feedback control system application, specific to some of the research that I've done in the past in my research lab. So the project that we're going to be discussing here is ambulatory load dosimeter measurement and feedback control related to seated posture. Now within this system here, this was a design project that we took all the way from initial concept through final product clinical trials and data analysis. So this is something that we could work and talk with as we continue on into ME curriculum, not only within the systems dynamics course, but as we continued into ME 171, your design of elements course, where we discuss all of these different design parameters. So within this system here, we had three major components. We had our load dosimeter, which is our flex sensor or bend sensor. We had the apparatus in order to attach it to the user, which is a neoprene belt here, and then we had our electronics box over here with some other sensors inside it as well. So within this system, what we're looking at is feedback control of seated posture, and we're using a load dosimeter in order to do the measurement for this. So the initial objective, again, was to develop a device for measuring and recording the lordosis, or curvature of the lower back, of the subject while they're seated. So within this, there's a couple different design objectives that needed to be met in order to meet the criteria for this project. So the first thing, we needed a device in order to measure the curvature of the lower back while the subject was seated. So two different sensors were utilized for this. We needed a load dosimeter that measures the curvature of the lower back, and we needed a tilt sensor built into our electronics box to tell whether the person was seated or standing. The next thing that we needed in our design objectives was the capability of storing data. So we had a buffer built into this here so we could store the data that could be then later uploaded for post-processing and analysis. This also needed to be user-friendly. We're giving this device for subjects to use for a week at a time with little instruction as to how to use it other than their first initial test meeting with us. So that being said, with having them for a week at a time, they also need to be very reliable and durable in order to make it through the entire test cycle without breaking and not have to switch them out all the time. So that was a very important part of our design criteria right there. And it also had to have the capability of giving feedback. So that's how it ties into what we're talking about now, is this feedback capability. So when the user is in a slouched position and seated, it needs to send them an alert, some form of feedback, and it needs to be in real time so they can quickly adjust their posture to get back into the correct position. So we did this with a couple different feedback methods here. We did an auditory, so you could hear it beeping. We put a cell phone vibrator in it, so you could feel it in case it was too loud. And then we also had lights on it as well, so you could visually see it. So three different methods of giving the user feedback. Other criteria here need to be comfortable for them to wear through a long work day throughout the week. Need to have the capability of determining if the subject was sitting or standing. So again, that went back to our tilt sensor. So we needed feedback from that sensor there to let us know how to acquire data. So there's two different types of feedback we're talking within this system here. The feedback to the user, which is what we're calling biofeedback, and the feedback within the system, letting the electronics know whether the person is sitting or standing and whether they're slouching or they're in correct posture. So all of those are different types of feedback that the system is utilizing. It also needed to have custom capability of setting limits by the user themselves. So for every individual, what they consider slumped and straight are different. So they need to have the capability of setting their own threshold so they would know when to set off the alarms to get that feedback. So you're not going to get that biofeedback until you drop below the threshold, and you're saying that it's going to keep feeding back and alerting them until they get back up into the correct posture position. Secondary to this, we want to take a look at that biofeedback to the subject and see, can we utilize that to train them to stay in better posture? You know, if we keep this feedback on them for a long enough amount of time, are they going to learn that, okay, as soon as I slouch here, I'm going to get beeped at, I'm going to get buzzed at, I'm going to feel vibrant, I'm going to see lights, so I have to sit up. Are they going to learn, okay, I don't want to slouch, I need to stay up in this position so I don't get that feedback, that alert system. So that was the second part of the study, is to see if we can utilize that biofeedback in order to train a person to stay in better posture once they stop using this device. So in order to do this, we developed test protocols, a whole clinical study that we utilized. I won't get into too much of that now. We'll just focus on the feedback control portion of this project here. So what I want to show in this one here is that calibration process where the user would set these level thresholds for their feedback. So the feedback to the system and the biofeedback to themselves. So they could go through and say, okay, this is what I consider here an upright, straight position of good posture. This is what I consider here a slouch posture. And you can see the curvature here, the lordometer is measuring that curvature of the lower back and how that changes for what they're considering a straight position and a slump position. So that's setting one of their sensors to know, okay, this is when I get feedback that I'm in a nice curve here and the curve is above some certain level, therefore I won't set off the biofeedback. Whereas if I reach down here, my curve looks more like this here from the lordometer, and my tilt sensor for the electronics that's sitting in my pocket say that I'm sitting and not standing, I will set off the feedback, the biofeedback to the user. So a lot of this control system design went into the electronics. So this is where we're talking back to our block diagrams. We talked about the disturbance coming in. Well, a lot of this data processing and a couple years worth of research actually went into isolating some of those disturbances that we talked about. So even though we just see it as one little D of S on our block diagram, this is something that is actually very, very important and can take a lot of time to really narrow down and figure out what are these disturbances. And in particular for this project here, we were getting some very strange signals that were all over the place that wasn't just our data that we were interested in. It was coming from the fact that we did not have a common ground within our electronics, and it was picking up, the sensor was actually picking up frequencies from some of the fluorescent lights in the room. So we were getting all this noise that was distorting the signals and the values that we were really interested in, all from just not having a common ground on the outside and a shield on the outside of our electronics wire from the sensor going back to our data acquisition, our electronics box. So that's where it took us a lot of revisions of this just to determine what that D of S was and how we could eliminate it. So that's where we talked about everything where we vary our input functions and everything else. And the way we varied our input functions was we set blocks with set amounts of curvature on our flex sensor. And that was our standard input. And we looked at it and said, okay, if this is sitting still and we know the curve is this, why is our data all over the place? What is this disturbance that we're seeing in here? So that's a real life application of how important it is and how difficult it can be to determine that D of S within our control system. So what I want to do now is take a little bit of time to talk about some of the data that we saw from here. And what I'm going to concentrate on here is not so much how it related to my research project here, but the benefits of having feedback and how it can help with your system here. So what we had here was we had two different groups of people that wore this device. One of the groups of people had the feedback turned on, and one of the groups of people did not. They just wore the device for the entire week, and we just recorded what their posture was. So we could see, okay, throughout the week, the people that are just the control group and had no feedback turned on, we didn't see any improvement in their posture. They continued to slump, and their slumping actually got worse as the time went on during the week. Whereas the feedback group, the group that had feedback to them, alerting them when they had poor posture, when they were slouching, we saw that as compared to the control group that did not have any feedback, we saw improvement in their posture throughout the week by alerting them, by giving them that feedback. We could change their behavior throughout the weeks. So we talked a little bit about our control systems and how if a system wasn't stable, we'd need to go back and make revisions to the electronics, the components, the portions of the system in order to make sure that it is stable. And that's what we're talking about here for this project, our electronics evolution. So if the system wasn't stable, we had the issues with the common grounding, the shielding, the noise, the disturbances, all of those type of things would cause us to go back and do some development. Now, the other part of this that comes into play that we'll touch on in other courses is the design criteria for this here. So it might have a certain size requirement, a certain weight requirement, a certain power consumption requirement, a certain cost requirement. All of those things are going to come into play as well, and we need to take those into account when we're designing our control system. If all of a sudden the end user, the company, whoever it is, decides that they want to have it need to fit in your pocket, then all of a sudden something like the original box design isn't going to fit in everybody's pocket, so we need to make a smaller design. Or if they decide, okay, we need longer battery life. No longer can we use AA batteries. They aren't going to last the entire week. We're going to need to switch to some type of lithium-ion battery. or maybe we need different types of tilt sensors. So maybe we need an external tilt sensor that's not just in a person's pocket, because not everybody sits the same way. Maybe we need to have a leg strap that goes around the user that they can wear for people who don't have pockets and want to put the electronics device in their purse or their clutch, or some type of bag that they have on them. Therefore, we're going to need some way of determining whether they're sitting or standing. So all this is kind of a back and forth that's going into not only our electronics and our device development in the design process, but also in the control system design as well, because as we change all of these things, where they're located and how they are, we're changing our entire block diagram and our system design, our system control design as well. So with that there, a lot of things that might change within that are the actual sensors you're using for a closed loop system here. So as we tested more things and we found issues, we moved to different sensors. So we start off with just strain gauges. Well, this might not be so comfortable for the user to wear. It might work great in our block diagram and everything's fantastic. We have multiple sensors and on paper it works well, but when we actually go out and test it in clinical studies, doesn't work the same. So then maybe we need something that's a little bit more comfortable for them to wear. So we switch to an existing process where we take the sensor out of an old Nintendo Power Glove. We utilize that and we find it's not super accurate, the wiring's not so robust. So then we go into a custom designed strain gauge with a conductive ink, where we custom have these built, and over time we find, okay, connectors have issues. We need to work on the strain relief of that there, so we figure out a new way to do strain relief there. Then we decide how it connects. This keeps pulling out, so therefore we need to go to a Bendix connector over here that locks in place better. So all of this stuff, even though it's part of the design process, again, it ties back into our control system, and how does this affect how we set up the controls? Do each of these introduce a new disturbance, or do they help minimize disturbance? They require a different type of input, an RFS function there. So our RFS and DFS may be directly affected by which sensors as we switch them in and out. Even something that may seem as simple as how does the subject wear of these devices can come into play quickly. If we want this sensor to measure the curvature of the lower back, we need to make sure it's adhered to the back tightly and it's not lifting off. So something that doesn't give, a stiff type of fabric, might not hold it in spot too long. Something that allows them to slide up and down too much might move the sensor where it is relative to the back. So over time, we had to figure out all this stuff. And again, back to our control system, how the device is acting is going to make a huge difference on how we design our control system, where it's centered. What's a threshold level for slump versus straight is going to change based upon where this is positioned and how stable it is to the user, and how comfortable it is also going to have effect on how often they're going to end up taking it off, move it, shift it, and that's going to change our data and cause errors within our control system there that need to be figured in. So we talked briefly about the durability, reliability when we were talking at the very beginning about one of the design parameters here. So these are all things that come into play, all issues that we're going to have. Maybe software related where we're seeing issues here where we're getting these big spikes. Now the question is, that's a disturbance when we're looking at there. Is that disturbance from faulty electronics? Is it from not having that shield wire and we're picking up signals from the ambient noise in the room? Did a wire break and we lost a ground there? Is the sensor coming off there and not sitting in the right spot? Is it moving around? Are there vibrations? Is there external noise? All of this stuff comes into play. So even though in the design process we're talking about design, modification, and troubleshooting, in the control systems process, this is something that's going to directly affect it as well. And we need to take this into account. If this is something that can't be fixed, and this is just going to be part of the system, there's going to be an error there, and we have to bring that in, then we're going to have to figure out in our control system, how do we account for that? How do we factor in that error? How do we factor in that disturbance? So what is helpful is some of these block diagrams. So understanding, okay, this is my sensor input. This is my sensor over here. I have two sensors. They're input here. They're going in here. This is really going to help us design our control system a lot. If we understand the physical block diagram, then we can use that to make a block diagram for our actual control system. So we have everything that we need here. We have our power requirements input here. We have our flex sensor or our load dosimeter. We have our tilt sensors to let us know if we're standing or seated. And what we can also utilize this for, as we saw earlier, the device is going to keep developing, keep moving forward, new revisions, new prototypes, new models of this here. So the next step in what I was working on, I wanted to take this to a smartphone application. So I'd take the data, and rather than have to plug it in, I can send it to an application on a phone where this is another form of feedback. So we already have the alert feedback, so you're hearing it beeping to let you know when you're slouching. We also have, then we have the lights, our LEDs down here that give you a visual alert, and we also have a cell phone vibrator that's giving you that feel, that sensory alert there. But we can also have now is we're realizing, yeah, those things are all great, but also everybody's got a phone on them or a smartwatch on them. If we can give them a fourth type of alert, a fourth type of feedback, maybe we can even improve posture more by giving them different types of feedback. So if all of a sudden they're used to, okay, I hear my cell phone or I feel my watch going off, now that we have a Bluetooth capability on this here, we can give them that fourth source of feedback in order to make this project a little better, minimize some of the errors that we're seeing just due to human error of them ignoring the cell phone vibrator, ignoring the beeping or the visual part. So we want to give them even more feedback to help improve the system. So this is here from our block diagram here. We go up to our physical prototype and relate it back. There's our tilt sensor. There's our flex sensor. There's our electronic control board. There's our Bluetooth here that goes back to our phone. So when we're talking about this here, there's two sensors, tilt sensor, flex sensor, three sources of feedback right now: auditory from the speaker or the headphone jack option, feel from the cell phone vibrator, and visual from the LEDs lights. And then we're going to go on to that fourth one where we're getting that smart feedback as well, either on the cell phone or the smartwatch.